Hello everyone, my name is Jackson Harris. I'm the reporter for Group 2. Last week we did lab 4 for the Rankine cycle. My other group members are Chris Carter and Parker. So, what is the Rankine cycle? It's basically a cycle used in generators and like power supplies where liquid, usually water, is boiled and condensed over and over into like changing phase from liquid to gas to run a turbine to get work out of it. So it starts with a pump where work is inputted into a system to pressurize the water, which goes into a boiler where heat is added to boil it off into a gas. The gas runs into the turbine to get work out of it, and then it's condensed back into water to go back in the cycle over and over again. This is the TS diagram for the cycle, 1 to 2 being for the pump, 2 to 3 being the boiler, 3 to 4 the turbine, and 4 to 1 the condenser. This is the experiment that we used, or the setup that we used. The big gold pipe is the condenser tower, the boiler is to the right, and then the turbine is in the center. This system did not have a pump, so it's not a complete Rankine cycle, but it gets through the first, those 3 sections of it. So the first step we did, we emptied all the water out from the previous experiments so that we could have a consistent experiment controlled with our own water that we added, 4,500 milliliters, into the boiler. We used liquid propane for the fuel, and we ran the system for about 10 minutes once it was at steady state. We started up and made sure that it was at a certain temperature, certain ampage, and a certain voltage, and then ran the measurements for 10 minutes. We would have gone for longer, but it stopped working at 10. So here we have the fuel flow versus time. That was pretty consistent over the whole thing until it stopped working at about 4.5 liters per minute. And then this is the boiler pressure and boiler temperature. And then turbine input and the output temperature and pressure. All of those are relatively steady state. These are the values so a steady state point was chosen at t equals 500 seconds. This is because it was in the steady state section of the graphs. Atmospheric pressure was assumed to be 101.3 kilopascals. The initial boiler fill amount was 4,500 milliliters, and then the rest of the values were found from the different graphs and sets of data. The steady state condensate amount was 400 milliliters. This was how much water was removed from the condensation tube at the end, and then the steady state boiler water used. That was the difference between the initial amount of water at 4,500 minus the 400, and then the 1,200 that was removed from the boiler at the end. So overall, the system boiled off and lost 2,900 milliliters of water throughout the system. And then the mass flow rate was about 0.006 kilograms per second. That was taken just from the amount of water taken from the boiler at the end compared with the initial and over the time that it was measured. So these are some of the properties found in the steam tables. The pressure and temperature was used to find the different properties of its specific volume, enthalpy, internal energy, and entropy. The pressure and temperature for the condenser for inlet and outlet, those were assumed based on an ideal system. So their values probably aren't exactly right, but they should be pretty close. And then for the calculations, these were the equations that were used. The boiler heat was the difference in enthalpy from 0.3 to 4, or 3 to 2. Turbine work was from 4 to 3, and then condenser heat was 4 to 1. And then the thermal efficiency was the work divided by the difference in heat from the boiler and the condenser times 100 to get a percentage. These are the experimental and theoretical values that were found. The boiler heat is pretty much the same. The turbine work was also pretty close, and the condenser heat was relatively close, but the small differences over the two create a theoretical thermal efficiency that's almost double the experimental value. This makes sense as you can't have an ideal system. There's always going to be losses, in whether that's friction or heat loss or things like that. So that's just generally like what happens in this kind of system. This is the turbine speed versus time, and then these are the voltage in amps over time. These look very messy, but if you look at the scale, it's still relatively close. This is just like zoomed in. So overall, this should be steady state. Some ways to improve this: adding more insulation to the system to reduce the heat loss could improve the system as a whole. You could reduce friction by like oiling the motor or like getting smoother tubes, less turns and things like that. You could add a pump to make it a full Rankine cycle, and then the condensation chamber let off a lot of the boiled water into the atmosphere. So that's there's a lot of losses through that. And that's about it. Any questions?